thank you for giving me this opportunity to present work I did with my collaborators here in Lecce, Matteo Beccaria, and also Francesco Galvano, who's in Torino. I live in Torino. And this will be about n equal to 2 theories, but a very specific sector in which we only consider the operators with large R charge. And we will consider them in a very specific limit, which is called a double scaling limit. So the first thing is, what is a double scaling limit? And the prototypical example is Hooft limit, where Hooft realized that we can, for an SUN gauge theory, we can take the limit where the gauge coupling is very weak and is very large, but we keep G square n a constant. And simplifications happen in this limit. Recently, another example which has been studied is the case of a QFT which has some coupling, and then there are, and it also has a global symmetry, and we consider operators which have a very large charge under this global symmetry. In one attractive setup for studying this kind of limit is the case of n equal to 2 superconformal theories in 4D, superconformal theories with 8 supercharges. And these are attractive because because of tools like localization, we have very good control over them. And the goal of this talk would be to exhibit some of the simplicity that emerges when we take this double scaling limit. And this will allow us to probe some of the massive BPS states in the theory towards the end of this, hopefully towards the end of this talk. So first, a very quick primer on two-point functions in conformal field theory. So if we consider a conformal field theory which is isolated, then the two-point functions are trivial because they just tell us what should be the normalization of primary operators. But on the other hand, if we have theories that allow exactly marginal deformation, they contain actually a lot of information because they are non-trivial functions of the exactly marginal couplings. And for the superconformal theories we will be considering, there's always one there's always at least one exactly marginal coupling, which is the complexified gauge coupling tau. So the setup we will be considering would be there's some primary operator O of x, and its two-point function has a kinematic factor which is fixed by conformal symmetry, and so is not very interesting. But there is this coefficient which depends on the gauge coupling. And I will abuse the terminology a bit to call this part, just GOO bar, to be the two-point function.
Sorry, but also the anomalous dimension can change during the flow.
I mean, that will not be an exactly marginal coupling, right? If yeah, in general, but in superconformal theories, this is actually protected. So for superconformal theories, this delta of O just depends on the R charge. So it will not change. It will not change on the flow. So delta of O is independent of tau and tau bar.
Okay.
So we will be considering, so that's like, the reason it is we're considering very special kind of operators. And these are generated by this trace phi to the k, where phi is the scalar in the vector multiplet. So this is in some sense the universal sector of the SUN gauge theories, which does not depend on the detail of the theories. And the webs of these operators parameterize the Coulomb branch of vacua. And the reason they are interesting is that due to supersymmetric localization, we have some very powerful results to calculate. to calculate quantities related to this Coulomb branch. And the reason is that for n equal to 2 theories, the partition function on for sphere can be reduced to a finite dimensional integral over Coulomb branch. So because Coulomb branch is parameterized by these traces, this is an integral over a matrix, which we call, so this is a matrix over a matrix M. And this only depends on that, and this integral only depends on the traces of M. I have called this MA here, sorry about that. But, and there is this Meyer, which I've called dA in square brackets. And because we have an integral that only depends on traces of A, this actually reduces to an integral over the eigenvalues of this matrix M, which I have called A mu. And the important thing to note is this vector in orange, which contains differences of eigenvalues. So what it tells us is that in this setup, the eigenvalues don't want to be very close together. And the appearance of this vector is a telltale sign that we're dealing with a matrix integral. And there's a lot of, and these matrix integrals are important in a lot of areas of physics, and they have been very well studied. So we know a lot of results about them. And so the idea now is to use this setup to include correlation functions. And we will consider a very simple sequence of operators which increasing R charge. And this the R charge is this n, and that operators are trace of phi squared to the n. And on S4, so this trace of phi squared is very special because this is a thing that appears here, trace of A square. It appears, it couples to the, it couples to the Yang-Mills coupling, this imaginary of tau. And so on S4, the correlation functions can be calculated using localizations. We have to compute some derivatives of the partition function with respect to tau and tau bar. And this turns out to be not diagonal. And so this is something which is very different compared to the flat space case. And the reason is that they are there's conformal anomaly. So although the matrix of flat space and sphere are equivalent, the map between operators on the two spaces is not trivial. And we need to perform a Gram-Schmidt orthogonalization on this series of operators we are considering. And that's another reason why they are special, because we can only consider their orthogonalization. We only need to orthogonalize them among themselves, and we don't need to consider other operators, which might have the same R charge. So, and we will study this in the double scaling limit. And where we have introduced a coupling kappa, which is 2 pi n over imaginary of tau. And we send n to infinity and the imaginary of tau to infinity, but we keep their ratio fixed. So a priori, it's not even clear that if this limit exists, and if it exists, is this something non-trivial? And localization is one path to answer this question, but it's complicated by the conformal anomaly. But this limit has been studied in specific cases where it has been found out that the answer is indeed yes. For example, in these papers, this limit does exist for SQCD. For the simplest case, which is SU2, we have a even better understanding of this. And we even know the results, which are non-perturbative in this coupling kappa. And the way they were proposed by Matteo Beccaria my collaborator, and then they were later proved by Grassi, Komargodski, and Tizzano, who realized that this Gram-Schmidt process, in fact, hides another matrix model. And as we will see, this observation actually generalizes to the higher rank case, and we are able to apply the power of random matrix theory to general SUN. So let's see how that comes about. So we define the n by n matrix, M of n, which is the matrix of these derivatives. And then the flat space correlator can be written as the ratio of determinants. And we can deform, so in this determinant, in this matrix, every element is an integral over Coulomb branch. What we can do is we can exchange this we can exchange this determinant for an integral of determinants. And when we do this, then again we see this vector, which we're seeing again, this van der Monde determinant. And this tells us that we are again dealing with a matrix model. And the eigenvalues of this matrix model are trace of AI squared. So after some calculation, we will see that we have an integral with some over this matrix with some potential v. The eigenvalues are trace of I square, so they are always positive. So we are dealing with an integral over positive matrices. This is called a Wishart-Laguerre ensemble. And the large n limit of this potential v can be determined from the interacting action of this theory, of the theory we are considering. And it turns out that if the rank of gauge group is greater than 1, so if we are considering SU3 and greater, then V contains higher traces of all orders. And this brings us back to the question of whether this limit exists at all. Because if these higher trace operators are not suppressed, then this limit can't exist. But it turns out, as we should have known from the earlier results, that in fact they are suppressed. But the second question is how much suppressed they are, because if they are too suppressed, they don't contribute. But they are suppressed just right, that they contribute at the same order as single trace operators. So in this case, we have this large n limit, but this large n limit is different from the standard 2 limit because it's not planar. It receives contribution from traces of all orders. And this can be seen in the super diagram picture too. And in fact, I'm not going to go into a lot of detail about this, but there's an excellent video poster by my collaborator, Francesco Galvano, which provides more details about the super diagram analysis. But what happens is that instead of being dominated by planar super diagrams, in this limit, the diagrams that dominate are the ones that maximize the genus at a given order in gauge coupling. So the first one loop correction is planar, but as long as one loop which corresponds to G angle square is planar. But the two loop correction has genus 1 due to the insertion of this box diagram. So the summary is we have a very efficient algorithm for perturbative calculation, and we can derive very long expansions like this. And this algorithm is completely generic. The only assumptions we are making is that we have that the partition function can be written as an integral over Coulomb branch, and we have a simple gauge group like SUN. And but non-planarity makes it hard to do some perturbative calculations, and we cannot probe the large kappa regime, which is in contrast to SU2. Remember, for SU2, this limit is planar, and we have much better control. And indeed, both of these papers find that that there are exponentially suppressed calculation in the case, exponentially suppressed contributions in kappa, which can be computed. So to see a more striking simplification, we turn to a different setup, which is one-point function in the presence of Wilson loop. So the basic setup is this. There's a Wilson loop of radius r, which we'll take to be 1, which is embedded in a plane spanned by x1 and x2. And we want to find out the one-point function of a chiral operator, which is inserted at this point x. And again, we have a kinematical part, which is completely fixed by conformal symmetry, but there is a coefficient which depends on the complexified coupling, actually just the imaginary part of it, and it's that which we are interested in. So what happens in that case? So the reason this is a nice observable, Wilson loop is nice observable, is that we again have a description using localization, which was the original motivation of Peston when he derived localization. It turns out that in the large n limit, this one-point function in the presence of Wilson loop is the same as another two-point function. So there is this operator which is trace of a squared to the n, which is the sequence of operators we are considering, and then there is trace of a to the 2n. And the large n limit of this two-point function is captured by a matrix model, which is very similar to the one we find in SU2. So there is a z effective, which depends on this which is an integral over one variable r, and there's this z1 loop part, which is r times a naught, where a naught is a fixed matrix, and it is the matrix that maximizes this trace of a to the 2n. And because of and then we have to go back and do the same process we did before. We start with this matrix, and we try to and we do the unmixing procedure. And in this case, we can actually find out an answer, which is very simple and allows us to compute the all order kappa, not at least conjecture the all order results in kappa, and the result is strikingly simple. So there's an integral over a variable t, and then there's this function j of t, which is the only theory dependent input, and this j of t this j of t has a very simple interpretation in terms of the symmetry of the situation we are considering. The SU2 like ZF is an integral over this line R of A naught in the Coulomb branch. And on this line, the webs of phi always break SUN to UN minus 1. The supermultiplets split, and as the representation of this UN minus 1, and the webs of phi give mass to some of the resulting fields. And each representation which gets mass contributes exactly one term to this j of t. And this term depends on the dimension of the representation, and j naught is a Bessel function. And this mass mr, so the only thing I need to compute this contribution is this mass mr. And this thing actually vanishes if the mass is 0, so the massless particles don't contribute. So let's take one simple example, which is n equal to 2 SQCD. There are two n hypermultiplets in the fundamental of UN. Each fundamental hypermultiplet splits into a fundamental and a singlet of UN minus 1. And at that point, kappa A naught, where kappa is the coupling and A naught is the point on a sphere, the mass of U in fundamental is kappa, is this, and uh, so the mass of has some mass. Similarly, the singlet has some mass too. Similarly, the vector multiplet also splits. There is a UN minus one unbroken gauge symmetry. And so this doesn't contribute. The gauge bosons don't contribute. And there are two massive W bosons, which have mass square root of kappa and over n minus one. And I can put together these three contributions to get out the final result. And this final result indeed contains both perturbative part and an exponentially suppressed corrections which are not visible to perturbation theory. So lastly, I will try to summarize and talk about some area of future interest. So the one takeaway is that leveraging localization and the power of random matrix theory, we can learn about the R-chart limit of n equal to 2 SUN theories. But this rather requires choosing the observables quite carefully. We chose these ON because of their simplicity. It turns out there are some other, there's at least one other class of such sequences that we can deal with the methods we have. But one open question is if there is a similar story for a generic sequence of operators which have large R charts. And then there's a special simplification in the case of Wilson loop, a one-point function in the presence of Wilson loop for SUN gauge group. And this simplification is that this large n limit is always planar. And this allows us to find out a very simple relationship between this two-point function and the mass spectrum of the theory at the relevant point in the moduli space. And another way these observables can be calculated for the case of SU2 is in terms of an effective field theory description, which I don't have time to go into. But maybe this, because the structure is simpler for the case of Wilson loop, maybe this sector is also described by such an EFT, and that's like maybe one of the things to think about in the future. Thank you. That's it for me.
Okay, thank you very much. Are there questions? Any question?
I might have a very naive one. Why these ON operators can only be diagonalized among themselves?
So so this is related to they have like a very special structure. I think I can give like two answers, and which are both related. So one is like when they can. So one is like they have like very special structure in terms of this toda lattice. And so if you go to this paper by Borgia et al., what they describe is that there is no fixed ordering for the operators. So to perform Gram-Schmidt orthogonalization, we first need to choose an ordering for the operators. So the Gershowitz et al. Choose an ordering which is ordered by the R charge, and if different operators have the same R charge, you can just order them as you like. But they point out that there is like, because of the total structure of these correlators, what you can do is you can exploit them, and you can choose these special toda orderings, which are that you first orthogonalize these operators. Then you orthogonalize, for example, some operator. Then you orthogonalize another infinite tower, which consists of some operator multiplying these operators. So this is a different ordering. And another way of, I think, like doing this might be that, so you Gershowitz et al. Like realized, oh, if you consider n equal to 4 theory, you can in fact get these infinite towers of operators, which are this times an operator, and these are orthogonal among themselves. This does not happen for the case of n equal to 2 theories. But the limit we are considering is very, very close to n equal to 4 theory, because we are taking coupling to be 0. So I think there's probably something which I'm less sure about, but I think there's something there too.
Thank you.
Are there other questions? Excuse me, where come from this matrix theory? I mean, how come from, what is the action on the matrix actually?
So you mean this V?
Yeah.
So you can see like that eigenvalues are trace of AI square. So what we can do is I can consider this trace of AI square as the radial direction in Rn, and then there are some angular variables. And to get the action, I basically have to integrate this Z1 loop, which comes from the definition of n equal to 2 theory, and I have to integrate them over this over these angular variables. And so this gives me and so they're basically the angular expectation value of this Z1 loop with some with a Meyer, which is determined by this part.
What I want to say is there any deep reason to expect this, or it just, how to say, as a matter of fact?
I mean, I would say that I don't have like a good answer to this question, but I think like the deep there would be a reason to expect that some such thing exists, because there were like prior calculations which told us that this limit is actually very well defined. So, but the question then would be like how general it is. And I think like this matrix, this connection to the random matrix theory basically allows us to answer that. I mean, I'm not sure I have answered your question, but